All right, ladies and gentlemen. Boys and girls. Children of all ages. All right, ladies and gentlemen. We are going to be talking today about the mole. We talked basically what the mole was last week. We talked about the mole is kind of like a dozen. So if I say dozen, you immediately think how much? 12. 12. Well, if you tell a science person a mole, they immediately think 6 times 10 to the 23rd. Technically, it's 6.022137 to the 23rd. I don't care about those extra digits. I would be happy if you just did 6 times 10 to the 23rd. It's a big, big number. Talked about how big. There's also a poster right there. There's a billion, million. It's 0.6 billion, million. It's huge. Now, what is the mole used for? Well, more than you think. It is a really slick ratio between things we can measure, grams, and things we can't measure, atoms. We can't measure atoms, they're too small. But we can use a ratio between grams to atoms, so if I want to know how many atoms I want to measure out, I can use grams. And that's what we're going to be talking about today, we're going to be measuring today. This is called Avogadro's number after this guy named Amedeo Avogadro. He did some work with gases and he came up with this crazy little ratio and said, hey, everything turns out to be about the same number. So we name it for him, Avogadro's number, 6 times 10 to the 23rd. Again, I really don't care if you remember this, but it's on the wall too. Avogadro's number, 6 times 10 to the 23rd. There you go. So just like if I asked you to go to the donut shop and get 3 dozens, you would come back with 3 times 12. If you wanted 3 moles, you would just multiply 3 times 6 times 10 to the 23rd, and you get 18 times 10 to the 23rd, or 1.8 times 10 to the 24th. Okay, make sense? So it's just like a dozen. It's a set number, 6 times 10 to the 23rd, just like a dozen is a set number. If I wanted to ask you for 4 moles, you just multiply 4 times 6 times 10 to the 23rd. Okay? Give me a thumbs up if that makes sense to you. Cool. All right. So, how many molecules is half a mole of molecules? 3 times 10 to the 23rd. How many is 2 moles?
2 times 1.2 times 10 to the
23rd. 1.2 times to the 24th, or 12 times to the 23rd. Okay, so very, very simple stuff. Okay, very, very simple stuff. So, what is it used for? It turns out to be a very, very useful tool. I have up here some silicon. If you don't remember silicon, it looks nothing like silicone, which is like a gooey, pasty stuff. Silicon is like bluish silver rocks, and they use it to make glass. So this is pure silicon, and I have 28.1 grams of silicon in this container. If you look at the periodic table lists the mass of silicon at 28.08, basically 28.1. The periodic table's mass, are you paying attention? Mm-hmm. The periodic table's mass is in grams per mole. It's called the molar mass because it is the mass of 1 mole of molecules. By weighing out 28.1 grams of silicon, I have weighed out 1 mole of silicon, which means I've weighed out 6 times 10 to the 23rd atoms of silicon. Oh, yeah, molar mass, the mass of 1 mole. Copper has a molar mass of 63.5 gram per mole. There's 63.5 grams of copper in here. How many moles are in here? 1. How many atoms are in here? 6 times 10 to the 23rd. See how that works? Same thing with tin and sulfur. I have 118.71 grams of tin in this container. And if you look at tin, it has a mass of 118.71 grams. I have, in this container, 1 mole. Make sense? So if I asked you to get a balloon and fill the balloon with 1 mole of argon, how many grams of argon are you going to put in the balloon? Argon's on the far right.
39.948.
39.948, yeah. So about 40 grams. So the molar mass on the periodic table is 40 grams per mole. So if I asked you to fill up a balloon with 1 mole of argon molecules or argon atoms, you would weigh it out so it was 40 grams heavier than the balloon itself. Does that make sense? And that's what we do. So later on, I'm going to say, okay, you're going to need 3.2 moles of this. You're going to be like, all right, mass multiplied by 3.2, weigh it out, boom, 3.2 moles. That's what you're going to be doing in a lab later on this week. Okay, questions? Yeah.
So 6 times 10 to the 23rd, is that the mass of an atom?
No, it's the number of atoms in a single mole. So just like a 12 donuts per dozen, it's 6 times 10 to the 23rd atoms per mole. It's the number of atoms in a single mole. Mm-hmm. So the great thing is, it doesn't matter what stuff you have. If you have a mole of calcium, you'll have the same number of atoms as if you have a mole of xenon. And very different properties, but mole is a mole. Just like if you had a dozen donuts, it'd be the same as a dozen peanuts. Make sense? Thanks. Okay, so if you understand that, then we can do some practice. The average atomic mass of carbon is 12 grams. What is the mass of a mole of carbon atoms? 12 grams. Yeah. What is the molar mass of copper? Find it on the periodic table.
65.
Yeah, about 63.5 grams per mole. So if I wanted, when I wanted to weigh out a mole of copper atoms, I weighed out 63.5 grams. Okay, cool? Easy so hard or hard so hard? So far. Easy? Okay. Question?
So, for like a certain element, does it maintain its molar mass when it changes, like state of matter, like from when it goes to liquid to?
Yes, it does. That's an excellent question. Yeah, the molar mass doesn't change during a chemical reaction or a physical reaction. A physical reaction is melting, freezing. A chemical reaction is burning. So the molar mass of the stuff doesn't change. The only time it ever would change is during a nuclear reaction, where we have nuclear decay going on. So yeah, excellent question. It doesn't change during a reaction. Other questions? Cool. Give me a thumbs up. You're ready to do some practice. All right. What is the molar mass of nitrogen? Now, nitrogen is the N in Brinkelhoff. Nitrogen is a diatomic molecule. If you're sitting in front, they're listed right there, Brinkelhoff. So, what is the molar mass of a mole of nitrogen molecules? So write it on your paper, and when you think you got a good answer, show your neighbor, and then see if your neighbor knows what he or she is doing. Boom. If your neighbor got a number that is larger than 10, raise your hand. Good. If your neighbor got a number larger than 20, raise your hand. Oh, that's good. Okay. Should be 28. Remember, nitrogen is 14 on the periodic table, Gesundheit. Nitrogen is 14 on the periodic table, but nitrogen is diatomic. What does di mean? Two atoms. So nitrogen will never be found alone because it's diatomic. If it can't find something else to bond to and make a compound, it'll bind to another nitrogen molecule and make an N2 element. Okay? It's never found alone. So if you try to weigh out nitrogen, it's going to be impossible to weigh out nitrogen atoms. You're going to have to weigh out an N2 molecule. Give me a thumbs up if that makes sense.
Yes.
All right. Here's another one for you. the molar mass of carbon dioxide? And it's exactly like it sounds, carbon dioxide. Which, while I'm thinking about it, if you're breathing out oxygen, what are you breathing? Or if you're breathing in oxygen, what are you breathing out? Yeah, that's what elementary school teachers teach you. It turns out you're breathing very, very, very little of carbon dioxide out. Unless you're running a marathon and you're huffing and puffing, most of the oxygen you breathe in, you breathe out too. Yeah. You only use about 5% of the oxygen you breathe in. Yeah. Unless you're like a marathon runner, you're using far less oxygen than you think. So, remember CPR where you do the chest compressions and you rescue breaths?
Oh, that's why that works?
Partially, yeah, partially. Mostly it's just to get the lungs moving, but yeah, it's partially why it works because you still have a lot of oxygen in your breath. If you want to find out exactly how much, we do have gas pressure sensors. Yeah. Okay, guys, I want to hear Scott, but I can't hear him because you're talking. Go ahead. Yes. Yes, you could. Because, again, unless you're running a marathon and you're really huffing and puffing and struggling to get oxygen, you are using only a small portion of the oxygen you're breathing in. Otherwise, we'd all be suffocating. Because there's no way we could vent. If we were all exhaling the carbon dioxide, the same amount of carbon dioxide as the oxygen we were inhaling, the room would have to have no roof or no windows, because we'd all suffocate otherwise. We'd all get oxygen hypoxia or carbon dioxide poisoning. We'd all pass out and die. So, but as it is, just having little cracks under the doors is just good enough. Yeah. Did you get 44?
Yes.
If you got a 44, give me a thumbs up. Okay, if you didn't get a 44, then I don't know what you would have done. But carbon is 12, and again, in chemistry, we put a subscript after the thing we're referring to. Okay, it's called a subscript, which really means writing below. So it's written halfway below the line. CO2 means 1 carbon and 2 oxygens. Question?
Like on a quiz or test, will we know it's diatomic? To be able, or we have to memorize?
Well, if you could probably see the board, but I would recommend you memorize it.
Memorize it?
There are only seven diatomic. It's a good question. There are only 7 diatomic molecules, and Brinkelhoff is a fun little mnemonic. So if you just remember those, like on a test when we're doing balancing and reactions, you just can just scribble Brinkelhoff across the front of your scratch paper at the beginning, and you're probably going to be in good shape. Question?
How do we know that's not 2 cobalts?
Oh, that's an excellent question. How do we know it's not 2 cobalts? Because cobalt is written capital lower.
Oh.
And that's a really good question. If you were wondering why there are no capital symbols, it's because it's capital lowercase for this exact reason. So if you see capital, you know it's 2 elements. That is a very good question. Which is why the only thing that's really tricky is iodine and chlorine. Sometimes the font of various things will show a capital, then that. That's carbon and iodine, but sometimes the font makes it look like that, like chlorine. So if you are ever unsure if it's carbon and iodine versus chlorine, please ask. Because sometimes the font of various tests and worksheets make it less clear. That's an excellent question. Okay, any other questions before we move on? More practice! Okay. Determine the molar mass of the following elements. We're going to start easy and get more complicated. I'm going to turn the lights on too so you can see your periodic table better. How about calcium? This is not a trick question. 40. 40, yeah. Calcium is on the left side of the periodic table. It's just 40. Just 40. Okay. Now, what about chlorine? Chlorine is the coal in Brinkelhoff.
It's 35.70.
Yeah. Now, the reason I mentioned chlorine is if you set this as 35, if you round and then multiply by 2, you're going to get 70. If you multiply by 2 and then round, you're going to get 71. I don't care. Either way, you're going to be in good shape. Okay? So if you're in the neighborhood, this is going to happen a lot. You're like, my friend got 300 and I got 298. Who's right? Probably both of you. Okay. So if you round at weird times, perfectly fine. Okay, give me a thumbs up if you're good so far. Question? Mm-hmm. A single chlorine would not exist.
Will be 35, right?
A single chlorine would be 35 or 35.5. So the diatomics will exist by themselves when they're in a compound. So the diatomic can't exist by itself in space, but it can exist in a compound. For instance, there's a common compound, it's CH3Cl. There's one chlorine all by itself, but it's in a compound with one carbon and 3 hydrogens. Okay. But you'll never see just chlorine hanging out by itself. If it is by itself, it's going to find another chlorine and say, I want to partner with you, make a diatomic molecule. Okay, next, calcium chloride. Yeah, let's just go ahead and bang it out on your calculator, on your paper. When you have an answer, show your neighbor. See if your neighbor agrees with you. If he or she doesn't, then please don't go to blows. You can settle it.
What's in this?
Sulfur.
No,
Oh, this.
Yeah.
Sodium polyacrylate.
Oh, that's cool. Is it like a slime?
Right now it's a slime, yes. We're going to be playing with it tomorrow.
How much is like drop that on your head?
Okay, I think from the chatter that you've got your answer.
Yes.
If your neighbor, ladies and gentlemen, if your neighbor got a molar mass of 100 or more, raise your hand. Cool. If your neighbor got a molar mass of 120 or more, keep your hand up. Nope. What'd you get? 111 or 110? Boom. Okay, next. H2O. Do the same thing. When you got a molar mass, show your neighbor and see if your neighbor agrees with you. All right. If you got a number larger than 10, raise your hand. Larger than 15? Larger than 20?
No.
Good. So hopefully you realize that the 2 was referring to hydrogen. This is H2O. 2 hydrogens at 1 each. 2 plus oxygen, 16, for a grand total of 18. Now, here's something new. In algebra, we put multipliers in front of parentheses. In chemistry, we put multipliers behind the parentheses. This is barium hydroxide. The OH is a special kind of ion called hydroxide, which we'll talk about in December, but this is barium hydroxide. And the 2 refers to whatever's inside. So give this one a whirl.
So,
Barium is on the left side of the periodic table, pretty far down on the bottom. Yes, you can approach it that way. Barium's on the other side of the paper. Don't carry it. Bring out Okay, I take it from the chatter that you've got an answer. If your neighbor has an answer that is larger than 100, raise your hand. Larger than 120? Larger than 130? Larger than 180?
nope.
Okay, good. So about 171?
Oh,
About 171? So again, there's a couple different ways to approach this. you can say, okay, I got 1 barium, then I have 1 hydroxide, which is 16 in 1 or 17. So you can say I have 1 barium and then 2 17s, or you can say I have 1 barium, 2 oxygens, and 2 hydrogens. That should work just fine, because math. Because math. Okay. Give me a thumbs up if you're ready for something a little more complicated.
Oh.
Yeah.
All right. This is iron sulfate, specifically iron 2 sulfate.
Chlorine. Where's chlorine? 56. Oh, iron.
151.
Iron's like dead center top of the middle periodic table.
Yes.
What am I doing? Sulfur plus
Okay. Sounds like in the chatter you're ready to move on. If you got a number larger than 100, raise your hand. Larger than 110. Larger than 120. Larger than 130. Larger than 140. Oh, we have a division. Okay, so we have iron, which is in the neighborhood of 55. Okay. Sulfur is 32, and then 4 times 16 is 64. Your number should have been 152. So if you didn't get 152, do you understand why you didn't get 152?
Yes.
I got one.
Okay, take a second. Okay, are there any questions? Okay, last one. The culmination and pretty much the most complicated thing we're going to do is putting parentheses in and subscripts in multiple places. This is aluminum sulfate. Take a look at aluminum sulfate.
Oh, wow.
Take your time. Treat it like an algebra exercise.
What inside the parentheses 3 outside? I'm just gonna do the inside first and I just multiply by 3. The correct answer is larger than 300. Okay, let's see how we did. Now, in processing this, there's a couple different ways to approach it. If it doesn't jump out at you, then just take it apart. So realize this is Al2 SO4, terrible O, SO4 which is Al, Al, SO4, SO4, SO4. So you can, so you can approach it this way, or you can say I got an Al, then I got an S, an S, and S. Then I have O times how many?
12.
12. So S times 3, Al times 2, S times, you get the idea. Okay. So regardless of how you do it, you're going to get the same answer because math. If you got a number larger than 300, raise your hand. Larger than 320. Larger than 340.
Yeah.
Larger than 360.
Yeah.
Good, okay. So 322?
Larger than 530?
Yeah.
I swear,
And,
Please, what did I do?